4E, which is fine. So really, we're trying to, we're talking about the gradient and direct proportion. So we want to really know the form of the equation that links the two variables that are directly proportional. So that's x and y. And we want to understand the gradient, that the gradient of the graph equals the rate of change of one variable with respect to the other. So we're talking about how much the rate of change changes. So for example, let me give you guys a little bit of a scenario on that one. If, for example, you're filling up a bucket with water, right? So, you know, there's water that is consistently, you know, you got to wash the car or something like that, right? And, you know, the water's coming out and, you know, you've got this bucket and, you know, it fills up, okay? Now that's going to, as long as the water's consistently flowing, you know, it will slowly increase, right, over time. Would you guys agree? Like the volume will keep on going up and up and up and up. So what we could do is we could measure it, well, when it was empty to when it got full. And let's say, you know, there's 10 liters. You know, you fill it up for 10 liters, okay? So here is 10 liters, okay? And let's just say that it took 5 minutes to fill up 10 liters. So we did 10 liters. It filled up. And it took 5 minutes to do that because you've got a really slow tap. Geez, that's a long time to be sitting at a tap, isn't it? For 5 minutes. Okay, so you're filling it up and it takes 5 minutes to fill it up. So if I wanted to graph this, this would be consistently going. After 1 minute, how many liters would be in there? Hopefully thinking, well, it'll be 2, because obviously, you know, it fills up at 2 liters per minute, right? Because the first minute 2, the second minute would be 4, the third minute, the third minute would be 6, the fourth minute would be 8, and the fifth minute would be 10 liters. So we can graph this. So we can do a quick graph of this one here. That should be a line. There we go, a line. Let's do a graph of this. And there my axes, right? Okay, just a quick little graph. And then what we're going to do is we can graph this. So this would be time. And this would be my volume. And this volume would be in liters, right? And time we said is in minutes. Now, the first part would be obviously 0. And then we've got 1, 2, 3, 4, 5, right? So we've got 5 minutes, 0 to 5. So after 1, we said we would have had 2 liters. So 2, 4, 6, 8, 10. And this is liters. So after the first minute, we would have had 2 liters. After the second minute, we would have had 4 liters. After the third minute, we would have had 6 liters. After the fourth minute, we would have had 8 liters. After the fifth minute, we would have had 10 liters. Now, what you'll notice is that that actually makes a straight line. Let's do this line. So that would have made a straight line, right? And it would have gone through. So, well, yeah, great. It makes a straight line, of course, because it's consistently filling up. What we're trying to relate to, so I'm just really trying to unpack one of these points here, which is to understand that the gradient of the graph, so we're talking about the gradient of this graph, okay, so the gradient of this graph, right, equals the rate of change of one variable with respect to the other. So it's the rate of change. So really what we're trying to say is this gradient equals the rate of change. The rate of change of what? Well, it equals the rate of change of volumes per minute, liters per minute. So what we're really trying to say is, well, what's the gradient of this? Well, it started off at 0, 0, right? Got to change this to that one. There we go, 0, 0. So this started off at 0, 0. And we ended up at like, well, after 5 minutes, we filled up at 10 liters. And it was consistently changing. What's my gradient of this graph? Well, it's rise over run. You can see the rise has gone up 10 and the run's gone up 5. So the gradient of this is the rise over the run. So it equals 2. But it equals 2 what? It equals, we're doing 2 liters per minute. 2 liters per minute. And that's what we're really trying to do. We're trying to, just show that what the rate of change is. So this point here, and what we're really trying to do is to understand the gradient of the graph equals the rate of change of pretty much the y variable with respect to the other. Because if you think about how do we calculate the gradient, right? We're talking about, well, how fast, and the top number is about how much it increases in this direction. Whoops, let's just go with this line. How much it increases here. It obviously overflowed here. I'm going a couple more liters. So it's gone up 10 liters, right? Which is this. It's really gone up 10 liters, right? And it took, because we always do rise over run, because that's how we measure the gradient. Remember, rise over run. It took 5 minutes. So it took 5 minutes. So what you will notice is that really, I mean, if you simplify this equation here, really what you're getting is when you look at it, you have 10 over 5 is 2. 2 what? Well, it's 2 liters per minute, right? Because obviously this will cancel out with this. This will cancel out that. That will leave us with 2. Well, it's 2 liters, and it's still per minute, over per minute. And this is exactly the same thing as travel, okay? If you guys, speed, right? You know how we talk about 60 kilometers per hour? Well, let's just say you jumped in a car, right? And you sped up to 60 kilometers an hour, and then when you're going 60 kilometers per hour, you just drive at 60 kilometers for an hour. Your speed, if you mapped your distance, it would be a straight line. And let's just say after an hour, 1 hour, you would have traveled 60 kilometers, right? And you would have started at 0. Well, if you think about, this is kilometers, and this is time, and this is in hours, okay? And this is distance, I should really say. That's distance traveled, and we did it in kilometers. So if you look at the gradient of this, well, this gradient is rise. It's gone up 60 over 1. So we've traveled 60 over 1, and that is kilometers per hour. Now, even if you think about this, right, if you go halfway, right, and we say, oh, well, what if you traveled half an hour? Well, if you went half an hour at 30 Ks, like 60 Ks an hour, you would have traveled 30 Ks, right? So this point here would be 0.530. Now, even if you think about this, if you go 30 divided by a half, that's still going to equal 60. And that's still 60 kilometers per hour, and that's how fast you're traveling. Another way I can show that is going back to here with this volume one. Obviously, you can understand the rate of flow. The gradient shows that it's how much it is changing. The gradient shows the value of this one, is simplified, of how much this is per one of these. That's all we're really doing. So how much this will change per one of these, because that's when you simplify it. You're going, well, really it goes, 2 liters per minute. If this was 1.5, it would be 1.5 liters per minute. But even if we looked at, let's just say we talk about, 2 minutes. At 2 minutes in, remember it was filling up at, it took 5 minutes to fill up. So if 2 minutes in, you'd expect it to fill up with 4 minutes, right? So let's go with 2, 4. Now, even if we just sort of stopped and said, well, from here to here, what is the rate it's flowing in at? Well, it's filled up 4, because remember to do the rise, on 2, and that's liters per minute. So really, that's still 2 liters per minute because it is consistent. So really, that's all we're trying to do in this. We're trying to actually understand what we're doing. I don't know why I was drawing that one. What we are doing in here, and that's really what we're trying to do in here. So on a 5-hour, so let's just have a quick look at this one. 5-hour, over 5 hours, Sandy travels 240 kilometers. So if she travels 240 Ks on 5 hours, we want to discuss her speed. Well, if you think about her speed is going to be in, well, how fast, considering she travels 420 Ks. So from here, she would have started at 0. And then after 5 hours, she traveled 420 Ks. Now, what's her average speed for the trip? So we're assuming that her average speed would be, well, if you just jumped in and you just kept on driving, that would be average, which probably didn't have it. But your average speed would be, well, you started here, it took you 5 hours. So it's 420 kilometers you did, I put the 2, over 5 hours. So this is how many kilometers per hour you did. 420 divided by 5 is going to be 82. How I did that so quickly is I just doubled this one and took the 0, 82 kilometers per hour. So what you've always got to recognize is when you divide these two and you find out the gradient, because the gradient is really your difference in your y, like your change in your y over your change in your x, because we're really doing your change in your y over your change in your x, your variables will be, well, whatever it was in your y over whatever it is in your x. And that's what this unit will be. And that's actually how we calculate speed. Is speed a rate? Yeah, speed is a rate because it's about how fast you're going per kilometers, how many kilometers you're going per hour. Now, you don't need to travel for a whole hour to get there. You could do a little bit. Draw a graph of distance versus time, assuming constant speed. Done that already because that's, 420. It would be constant. Where does your graph intersect the axis and y? Well, it would intersect the axis at 0, 0, because obviously when she started her trip, she started at 0 kilometers, right? That's why. Find the gradient of your graph. What do you notice? Well, the gradient of the graph is always going to be 82. You could choose any point on here. It would be rise over run. So she's speeding if it's in an 80 kilometer zone, and if it's in a 100 kilometer zone, she's driving really annoyingly slow. So that's sort of where we're at. Find a rule linking distance and time. We found the rule, which is how fast you're going kilometers per hour. No, sorry, the rule would not be that. The rule, I should say, that would not be the rule. The rule would be not that at all. The rule would be this. The rule would be linking distance and time. So the travel of distance, my distance would equal 82 times t, because I'm doing 82 kilometers per hour. So if I go 1 hour, I would have gone 82. If I've gone 2 hours, I've gone 164. If I go 3 hours, I would have done 8, 16, 24, 246. If I go 4 hours, I would have gone 8, 16, 24, 30, 328. And then if I've gone 5 hours, I would have gone 420. So you can see that for every hour I put in here, it's going to put me into distance. It's going to give me a distance where distance is kilometers. So I would have write where d equals distance, d equals kilometers traveled, t equals times in hours. I should define my variables. So I hope that helps a little bit. So that's sort of where we're going on that one here. So really, we're looking at the origin. The gradient is really the rate of change, and it's going to be, because we do y over x, it's just this per this. The rule is always going to be y equals mx. Well, not always mx plus, it could be mx plus c. But if it starts at the origin, obviously the y-intercept 0, so it's really just plus 0. And that's why it shows the gradient there. So if I look at this graph, I'm looking at, well, how fast do I travel? I'm going 10 kilometers per hour, right? If I do 2 hours, I'm going to go 20. If I go 3 hours, I'm going to go 30 kilometers. 4 hours will be 40. I can choose any of these points and I can actually figure out what the gradient is. I mean, they don't even need to be exact values. 15 divided by 1.5 would give you still 10. And that's 10 kilometers per hour. State how far the cyclist has traveled after an hour. So we can just look here. It's 10 kilometers. After 2 hours would be 20 Ks. After 3 hours, 30 Ks. 4 hours, 40 Ks. State the speed of the cyclist. It is 10 kilometers per hour. We can just figure out the gradient. Find the gradient of the graph. It's 10 because that's the gradient. We just figured it out. It's exactly the same thing. What do you notice about your answers from B and C? Oh, they're the same because the gradient shows the rate. That's what we're trying to show. The rule linking the height of a plant and its time. Wow, this is cool. Where h equals 5t and h is millimeters and t is in days. Oh, that's growing pretty quick. So that means really, if you think about this, t is in days, h is millimeters. So what's happening? So every time I want to increase t by 1, it's going to go up by 5. So it's growing 5 millimeters per day. That's how I read that. Find the height of the plant after 3 days. Put in 3 here. It's going to be 15 millimeters. Find the time for the plant to reach 30 mil. Let's do this one. So if you think about this, all we need to do here for this one is, for this first one, to find the height of the plant after 3 days. So if I go height, I don't want that big bold one. If I go height equals 5 times 3, because don't forget t is in days and we've got days here. So that is going to be h equals 15. So it's 15 millimeters because h is in millimeters. Okay. Find the time for the plant to reach. So that means, well, if it's gone 30 millimeters, that means H equals 5t. What information do we know? We know the height. So I'm going to substitute that in. So 30 equals, and I should be working down line by line. I might just do work down line by line. 30 equals 5t. I'm going to divide 5 on both sides. So t equals 30 on 5, which would leave me with t equals 6. So it's been 6 days. And if you think about 6 days, oh yeah, 6 days, 5 millimeters a day, that would be 30. If it's 10 centimeters, don't forget it's 10 centimeters. I need to convert it to millimeters because this equation's in millimeters. So 10 centimeters is actually 100 millimeters. So the height is 100 millimeters equals 5t. So now you divide both sides by 5. And you'll find t will equal 20. Yep. 5 is 100. T equals 20. And that's where we get there. So that's 20 days. We should give units to that. 20 days, 26 days, and so on. State the missing values for H in this table. So this is still, because this is part C, this is still referring to question 2, okay? So until you change the questions, everything still refers to all the information at the top. So, well, when there was no days, I mean, the height of it was nothing. Obviously, the seedling was still in the ground. That kind of makes sense. Because we're probably talking about seedling. After 1 day, it's going to be 5. 2 days, it's going to be 10. 3 days, it's going to be 15 mils. 4 days, it's going to be 2 centimeters. Yay, it's growing. Pardon me. So there you can see it's obviously increasing 5 millimeters per day, hence the rule is there as well. Choose the correct graph that matches the information above. Okay, so that would obviously be this one here. Because it's, it didn't start off at, this would indicate that it started off at 1 mil, which isn't right. I mean, not even the scale's right. Find the gradient of the graph. Well, the gradient is 5 because it's going 5 millimeters because it's rise over run. 5 millimeters per day is what it grows at. So yeah, but the gradient would be 5. But if we wanted to talk about what the rate is, I would say the rate of the plant's growth is 5 millimeters per day. So the rate and the gradient are pretty much the same. And that's where I was trying to really, I suppose this is one of the key points to understand the gradient of the graph equals the rate of change of the y variable with respect to the other. So how I actually read this, just to sort of summarize up, is, it's not the one I wanted. That's not the one. Just did the same thing twice. Okay. How I was trying to summarize up is really the gradient of a graph. Okay. So once you got a gradient of a graph, it really represents the rate of change. Okay. So if you do, your rise over your run, we're talking about rise over run. So, if you've got, for example, that rise over run would have been 5 and it would have been the rate of change of one variable, I would actually say the rate of change of the y variable over or with respect to the x variable. So y would be 5 millimeters per day. And that's sort of where I'll be sort of changing that. Yeah, so that's really probably the main key understanding here. To understand what it means for two variables to be directly proportional. If they're directly proportional, it has a consistent rate, okay? To know the form of one equation that links two variables that are directly proportional. So to be able to use the constant rate of change in worded problems and sketch a graph and form linear. So that's sort of where we're at. So this is a lot of this stuff is kind of like physics, it is a bit obscure. It is kind of like, when you're doing distance and time, it's a big thing. That's a huge mathematical concept where we gradient, we can do differentiation, which is what you do in your 11 methods. You're trying to look at actually the gradient and you derive the graph, which is like a whole new world of maths that got discovered because of this. Yeah, so there's a whole, this is just an awesome area of maths and physics and everyday life and projectiles and things like that. So it's really, I think it's quite amazing. So when you're mapping things out though and looking at a linear one, that's sort of where we're at. So yeah, that's pretty much where I think I'll leave it for this recording anyway. I mean, if you start looking at some of these questions, a 300-litre fish tank takes 3 hours to fill from a hose. What is the rate at which the litre is poured into the tank? Well, if we want it in hours, it's obviously going to be 100 because the gradient would be 3 divided by 3 would be 100 because it would have started at 0, 0. It would be 100 litres an hour, right? So if we did this and I drew like a quick graph of it, it would be would have a graph. It would have started at 0, 0, over time, would have gone up to this point here, and this point here would be, you'd have liters on this side, obviously. So it'd be 300, 3. So the gradient of that is 100, right? So it's like 100 liters per hour. Now, if you want to do it minutes, you'd have to change that then to 180 minutes, right? Then it would be 300 divided by 180. And I just love calculators for this reason. So if we did 300 divided by 180, so that would be filling up 1 2/3 liter a minute, right? Or 1.66 liters per minute. Or 5/3 of a liter per minute. So that's how fast it's filling up. So I mean, if we wanted to know what it was, how fast it was filling up in liters per minute, well, what you've got to do is you've just got to change your graph, really, or you just change your values. So if you think of your graph, it would have been, like this. This would still definitely be, 300. Whoops, I did my numbers around the wrong way before I realized this would still be 300, right? I did this the wrong way, sorry. That would be 3 hours. So that would have been 300, which is rise over, and this would be 0, 0 because that's where it starts at. The rise would have been 300, so it would have been 300 over 3. And don't forget, this is liters per hour. Therefore, that is 100 liters per hour, right? Now, if I want to figure out how fast it was filling up for liters per minute, okay, I would then have to go, well, it's 300 liters. And how long did it take to fill up? It didn't take 3 hours because we got to change this to minutes. It took 180 minutes, which is the same thing as 3 hours. Okay, so that would be 300 rise over run. 180. Notice now we're going to draw minutes. Now notice I write min because m is typically represented as meters, and then you'd find that would simplify down to 5/3 liters per minute. Okay. Now, if I wanted to know how many milliliters there were per minute, well, then I'd need to change this to milliliters. So 300 liters would be 300,000 milliliters. Again, I can just find out the gradient between any 2 points. So it's going to be 300,000 over 180. So that is going to be 5,000 thirds milliliters per minute. Which is approximately, what are we looking at? 1,667 milliliters per minute. Or you could even do seconds if you wanted, but then I'd have to go 180 times 60. I could figure out what that is. I'm going to get out my calculator now because it's just bothering me. So it'd be 300,000 divided by, what have we got? 3 hours. There's 60 minutes in an hour, in an hour, and there's 60 seconds in a minute. So 3 hours, 60 minutes in an hour, 60 seconds in a minute. And that would be filling out at a rate of, long behold, 27.7 milliliters a second. That's pretty slow. All that to fill up a bucket, huh? So next time when you go to wash someone's car, you can think about that, and hopefully it will be going a bit faster than that. That's really slow. No wonder it took 5 minutes to do it. Hopefully it gives you a bit of an idea about speed and time and things like that, and gives you an idea. It is a really abstract thinking for that. It does take a while to get your head around it, and it is quite different. But yeah, good luck with it.